In this lecture, we are going to see other two mode of convergences. First one is convergence in Rth mean, and second one is convergence in distribution. So, what is the Rth mean convergence? Again, the setup is as before that all the concerned random variable are defined on the same probability space SFP. So, Xn, the sequence Xn defined on the probability space SFP, and X is also defined on SFP. Now, for any R in the set of natural numbers, we say that Xn converges in Rth mean to random variable X if I find out the absolute moment of Xn minus X, absolute Rth moment of Xn minus X, then if this moment converges to 0 as n goes to infinity, we say that the Xn converges to X in Rth mean. Okay, so I have to find out expectation of mod of Xn minus X whole to the power R. And if this, note that again this is a sequence of real numbers because expectation is a real number. Once I take the expectation, it becomes a sequence of real numbers, and this sequence depend on n. It also depend on R also, but R is anything fixed in the set of natural numbers. So now it is a, if I fix R, it is a basically sequence in n, and if this sequence converges to 0 as n goes to infinity, we say that Xn converges to X in Rth mean. R is any fixed number in the set of natural numbers. Okay, so let us take example. Example is as before that same probability structure we have taken. F is 0, 1. F is Borel sigma field on the interval 0, 1. P is uniform probability on 0, 1. Measure and probability basically the same thing. So uniform probability on 0, 1. And the Xn is as before, it is 1 on the interval 1 by n, on the interval 0 to 1 by n, and it is 0 otherwise. So in this case, if I want to check that whether Xn converges to X in Rth mean or not, we are basically take R equals to 1. We are basically going to take R equals to 1, but other R will work in the similar fashion. We will do the R equals to 1, and we want to check that if Xn converges in first mean to 0 or not. Okay. And it can be checked very easily because if I take R equals to 0, this quantity is basically expectation of Xn minus X, mod of that, and then take the expectation. Now you see that X is 0, so that basically means expectation of mod of Xn, and Xn is 1 on the interval 0 and 1 by n, 0 otherwise. So this expectation of mod of Xn is nothing but 1 times probability of the interval 0 and 1, 0, 0 and 1 by n. So that basically this probability is 1 by n. So this expectation turns out to be 1 by n, and that quantity goes to 0. That implies that Xn converges to 0 almost surely. Xn converges to 0 in first mean. Okay, so Xn converges to 0 in first mean. Clear? So that means that this random Xn, which is basically 1 on the interval 0 to 1 by n and 0 otherwise, this converges to 0 almost surely, converges to 0 in distribution, converges to 0 in the first mean. In fact, if you have a R here, see the scenario will not change. If you have a to the power R here, this expectation still remains 1 by n. So for any value of R in the set of natural numbers, Xn, this sequence of random variable Xn converges to 0 in Rth mean. Okay, so next one is basically sequence convergence in distribution. So convergence in distribution, the definition goes like this. Xn is a sequence of random variable and X is a random variable. In this case, Fn is basically nothing but the distribution function of Xn. So F1 is the cumulative distribution function of X1, F2 is the cumulative distribution function of X2, F3 is the cumulative distribution function of X3, and so on and so forth, and F is the cumulative distribution function of X. The definition goes like that. We say that Xn converges in distribution to the random variable X if Fn converges to F pointwise as n goes to infinity. Okay, if Fnx converges to Fx pointwise as n goes to infinity, for which point x, and this convergence has to be true for all x where f is continuous. So I need to find out where this f function is continuous, this function is continuous, and I need to check whether this convergence is there for all x which is a continuity point of this function. Okay, this cumulative distribution function, the cumulative distribution function of x. Okay, if this convergence is true for all continuity point of the function f, we say that xn converges to x in distribution. Okay, so definition is okay. Now two things I should discuss here. First thing is that in the previous three, in the definition of the previous three modes of convergence, we have to assume that all the concerned random variables are defined on the same probability space. Why? The reasons are basically nothing but if I do not, for example, in case of the almost sure convergence, if I do not assume all the random variables defined on the same probability space, then the probability, first of all, if the S is different, this set does not make any sense. If the S is different, this set does not make any sense. Then if the sigma field and P are different, then this probability does not make any sense, even if S are same. So that's why you have to have all S, F and P has to be same for all constant probability, all constant random variables. Similarly, this is true for here also, because if anything is different, then this probability does not make any sense. Similarly, the expectation also. For the case of the mean convergence also, this expectation does not make any sense if all the constant random variables are not defined on the same probability space. But in case of the distributional convergence, this condition is not needed, because it does not matter on which probability space xn or x are defined. I have the distribution function, and distribution function always a function from R to R. Okay, so that means I can talk about this convergence does not matter on which sample space x1 is defined, on which sample space x2 is defined, on which sample space xn defined, and so on and so forth, and which sample space x is defined. So it does not matter in this case, because I am talking about the convergence of the distribution function in this case, cumulative distribution function in this case. That's why this restrictions is not written here, that all the constant random variable is defined on the same probability space, and this makes this convergence is more flexible, and that's why this convergence, the convergence in distribution, is used in many places. Okay, one point. The next point is basically that this odd assumption, that odd thing kept in the mind, that x, this convergence has to be true for all x where f is continuous. So this convergence I need to check for all continuity point of capital F, why this condition is kept. Okay, so these two things, first thing is already been discussed, that this is a more flexible one, and that's why it can be used in many different scenarios, and it is a very important mode of convergence. Why it is important, I am coming to this point. One, and the second point I need to discuss, that why this kind of condition is kept there, that I need to check this convergence for all the point where this function is, that f function is continuous. Okay, so these two things I discuss one by one. So first thing, why this is helpful and what is the main use of the distributional convergence and distribution. The main use is that if this f is continuous, this f, suppose this distribution function is continuous for all x belongs to R. So this f function is a continuous function over R. So what does this mean? This means that if the distribution of xn converges to x in distribution, then this convergence has to be true for all x in R, if this f function is continuous everywhere. Okay, so what does this mean? Now this means that if I take n is very large, then the distribution function of xn, for large n, the distribution function of xn can be approximated by the distribution function of x. Okay, so this is basically the use of the distributional convergence, that if the distribution function of x is very complicated, but if I can see that this distribution function of f actually converts to distribution function of xn actually converts to the distribution function of x, and the distribution function of x is continuous, then the distribution function of xn for large n can be approximated by the distribution function of x, which is capital H. Okay, and that basically means that if I try to find out the probability that xn lies between A to B, obviously this is basically distribution function at the point B minus distribution function at the point A, and which can, if f is continuous, if a capital, as I assume this capital F is continuous over R, so that probability that fn B minus fn A can be approximated by fn B, FB minus FA. So what I am meaning is that I am trying to tell is that, well, if F is continuous, on R and Fn converges to F, or I write it in the other way, and Xn converges to X in distribution, that basically means that Fn for large n can be approximated by f. Okay, so that basically means that if I try to find out some probability like a is less than xn is less than equals to b, which we know that it is nothing but the distribution function of xn at the point b minus distribution function of xn at the point a, and because of this approximation can be done, this thing can be approximated by f of b minus f of a, and this is helpful if you have this kind of scenario where fn is quite complicated, so computation of this one is maybe very difficult, but f is much simpler and the computation of this one is much easier. So in that case, if n is large, this probability can be approximated by this probability, this quantity. Okay, so this is one of the main use of distributional convergence. Okay, this is the main use of the convergence in distribution. Let us now discuss why this condition is there, that this convergence has to be true for all x where f is continuous. Okay, why this condition is true is needed, that we are going to discuss with the example 4.6. So in the example 4.6, we are considering a sequence of random variable xn where probability that xn equals to 1 by n equals to 1. So that means x1, probability that x1 equals to 1 is 1, probability that x2 equals to half is 1, probability of x3 equals to 1 by 3 is 1, and so on and so forth. So that means you can think of that the sequence of random, I mean it's not exact but loosely speaking, that sequence xn is equivalent to the sequence of real number 1 by n. Now we know that 1 by n converges to 0, so that means xn should converge to 0 in distribution, right? First of all, xn should converge because it's equivalent to 1 by n. 1 by n converges, and then 1 by n converges to 0, xn should converge to 0 in distribution. Okay, so let us check that whether this is true or not in this case, whether xn sequences, this sequence xn converges to 0 random variable in distribution or not. Okay, so to that what we need nothing but we need basically the distribution function of xn and the distribution function of 0. Okay, so distribution function of xn is nothing but 0 if x is less than 1 by n, and it is 1 if x is greater than equals to 1 by n. Okay, so now first we need to check, and on the other hand, the distribution function of 0 is basically 0 if x is less than 0 and 1 if x is greater than equals to 0. Okay, fine. Now let us check that if this function, this sequence of function converts to this function pointwise or not. Okay, so for this one we have this distribution and we check that how that this thing happens, that the pointwise convergence is there or not. So that means basically for fixed x less than 0, x less than 0 means x is less than 1 by n for any value of n. So this implies that x is less than 1 by n for all n greater than equals to 1, and this implies that distribution function of xn at the point x where x is less than 0 is equals to 0, which converts to 0 as n goes to infinity. Okay. Next, for fixed x strictly greater than 0, for fixed x strictly greater than 0, note that I can find out n naught. Here exists a n naught, obviously belongs to the set of natural numbers, such that 1 by n is smaller than x for n greater than equals to n naught. Okay, so whatever x greater than 0 I take, I can find out n large enough such that 1 by n is less than x. That is basically the main thing. And once this happens, that means basically this x after some n, after n naught greater than equals to n naught, this x belongs to this range. That means the distribution function after n naught will be equals to 1. So that this implies that the distribution function of xn at the point x will be 1 for n greater than equals to n naught. And this implies that distribution function at the point x converts to 1 as n goes to infinity. For any fixed x greater than 0, distribution function of x converts to 1 as n goes to infinity. Okay, so greater than 1, less than 1 done. Only thing left is for x equals to 0. And for x equals to 0, again 0 is always less than 1 by n for all n greater than equals to 1. This implies that the distribution function of xn at the point x is 0, at the point x converts to 0 as n goes to infinity. So that means the function fnx converts to a function maybe I call gx, where gx is 1, gx is 0 if x is less than equals to 0. For less than equals to 0 it is 0. For strictly less than 0 it converts to 0. For x equals to 0 it converts to 0. So less than equals to 0 it converts to 0, and for x greater than 0 it converts to 1. Right? So this converts to this as n goes to infinity, and this is a pointwise convergence. Now note that gx is not a distribution function because at the point x equals to 0, this is not a right continuous function. So clearly this is not a continuous function. But on the other hand, you can see from here that fn converts to fx also, where fx is given by 0 and 1 if x is strictly greater than 0, and if x is less than 0 here, x is less than 0 and x is strictly greater than equals to 0. Okay, x is strictly greater than or equals to 0. So and this convergence is true for as n goes to infinity for all x belongs to r minus 0. At the point 0, this convergence is not there because at the point 0 fn converts to 0, not 1. But if I remove the point 0 from here, that fnx converts to fx, and note that 0 is the point of discontinuity of x. Okay, so that means if I remove this condition from the definition, then this function does not converge to this, because at the point 0 this sequence does not converge to this sequence pointwise. But obviously if I keep this condition here, then at the point 0 I do not need to check, and except the point 0, everywhere this function is continuous, and for every point where x not equals to 0, this sequence of function converts to this function pointwise. Okay, and that's why this condition is kept here. If I remove this condition, this sequence of function does not converge to 0, whereas if I keep this condition here, this sequence of random variable converges to 0. Okay, and this is the reason, and in many cases this works very well. That's why this condition is kept here, and we say that xn converts to x in distribution if the sequence of distribution function of xn converts to the distribution function, cumulative distribution function of x pointwise for all the points where this f function is continuous. Okay, I hope this why this condition is kept there is fine. This is one of the example. This kind of example can be seen with other kind of sequences also, but this is a very obvious example where this extent should convert to zero. But if I remove this condition from here, then extent does not convert to zero in distribution. But if I keep it, then extent converts to zero in distribution. Okay, so that's why this particular thing is kept here. Okay, with this lecture, I stop here. In the next lecture, we will see some relationship between these four modes of conversion. Thank you for listening.